So I will now introduce Professor Jacques Magnaudet very briefly. He has been associated for a long time in IMFT, which is the Institute for Fluid Mechanics in Toulouse. It's a big institute which does lots and lots of fluid mechanics. He is a CNRS researcher, senior researcher of the exceptional class over there. He has, interests in these very hard fluid mech problems, primarily bubbles, drops, and particles and their dynamics, one which he'll be talking about today. A small part of his work he'll be talking about today. He also does like turbulence of the non-standard kind in inhomogeneous situations. For example, like what's the turbulence like below surface waves? So he asks all these very hard questions, and he knows a lot about so many aspects of fluid mechanics. He is what I would term an intellectual powerhouse. So he has got many awards and he's been invited to many important lectures. He's a fellow of many international communities such as the American Physical Society, the European Mechanical Society. I'm not listing all of these things, but also he chairs many important boards which decide on the very big international conferences in this area. So I will just end by saying that he is an editor of several journals. In particular, he is an associate editor of Journal of Fluid Mechanics as well as Journal of Fluid Mechanics Perspectives. So before we begin the lecture, I will request Professor Amit Apte to give a small memento to the speaker.
So sorry for the short interruption. And so thank you very much, Rama, for your very kind, maybe too kind introduction, and also for inviting me here. I'm really glad to be here today. Actually, it's my first professional visit to India, not my very first visit to India, but the first professional one. And I am really extremely glad to be here. And I must say that I've been impressed by all the vibrant activities I've seen over these 2 days. And well, I think ICTS is doing very well. So you gave an overview of all your outreach activity and scientific activity, etc. So I think this is really a great center. And I must say that I'm a little bit jealous that no such a center exists in France. Anyway, so, okay, so I will today speak about some stories about the falling and rising of freely moving disks, rising or falling under gravity. Actually, well, this is not the very last work we have been doing in Toulouse, but this was selected by Rama and her group. Actually, we have been playing with that for probably almost 2 decades now. So I'm not going to summarize what we did over the last 2 decades, but I will give you first a little bit of background. Actually, this is a subject that goes back very far in the history. Probably the first writing about this topic is due to Leonardo da Vinci, because Leonardo reported in several manuscripts his ideas about what happens when you release an air bubble at the bottom of a tank and you let it rise under the influence of buoyancy. And so, of course, he observed, as any of us, that under certain conditions, the bubble doesn't want to rise in straight line. Rather, it decides, for some reason, to rise either by performing zigzags like this, or by describing spiraling trajectories. And so Leonardo made some conjectures about the reason why the bubble chooses to do so. Actually, at that time, he didn't have the notion of a force. This came later with Newton, but he made some interesting conjecture on that. Anyway, and then speaking about Newton, Newton came about 2 centuries later, and Newton did experiments by himself. Actually, he did experiments by climbing to the dome of the Simple Cathedral in London, of course. And from this dome, he released a variety of spheres, some made of rocks, some made of glass, etc. And he observed the time they needed to reach the ground. And when he got too old, actually, to climb to the dome, he sent his collaborator, this guy, who was originally from France, Chevalier des Aguliers. And this guy climbed to the dome, and he released also spheres, and not only spheres, but also inflated bladders. And these inflated bladders, you can think about them as very light spheres. And so he released them from the dome. Again, he observes the time they need to reach the ground. And he also observes that these bladders, they actually experience some lateral excursions. And Newton, in the Principia, made some remarks about the fact that presumably these lateral excursions had something to do with the fact that the time required by this light sphere to reach the ground was larger than the one required by heavy spheres. So this was, in a way, the down of the subject. And by the way, if you have the opportunity to read this book, The Down of Fluid Dynamics by Michael Eckert, I strongly recommend that you have a look at least at some chapters of this book. This is a very nice book about how fluid dynamics was settled, especially in the 18th and 19th century. Okay, so here is the modern view of the subject. So these are two movies coming from our lab. So on the left, you see a probably 2 or 3 millimeter size bubble, which is rising in a tank. And on the right, you see a disk, which is also rising. Actually, you don't see it rise because actually the camera is traveling with the disk, so it seems to be more or less fixed. But what we did with this disk actually is that we put some dye on it in order to visualize the wake. And of course, you see that there seems to be a close connection between the motions, the lateral motions of the disk and the vortex shading in its wake. So there is clearly a connection, but we'll see how close this connection is later. Okay, so this is the modern view of the thing. And actually, regarding specifically disks, the modern story of this disk topic came back to the early 60s, in which there was a team in US that performed very nice dye visualization of the wake past freely falling disk. Then another group was able to draw the various stages of a disk fluttering or tumbling in a tank of water. And then, well, some decades later, another group was able to draw this phase diagram in which actually they were able to identify 4 distinct regimes. So what you see on the horizontal axis is the Reynolds number, which is a measure of the relative strength of inertia and viscous effects affecting the system. And on the vertical axis, what you see is the ratio of the inertia of the disk to that of the liquid that surrounds it. Okay? So the larger this I star, the larger the disk inertia. And so you see that they were able to identify 4 regimes. In this regime, the disk just falls on, along a straight path. Then here in that regime, the disk is fluttering like this. Then on the top of the graph, the disk is tumbling, so it performs full tumbles. And in between, they were able to identify a chaotic regime here. Okay, so this was the picture at the end of the last century, we would say. And we also did some experiments with disks. And for instance, this one, actually, in which we consider 2 disks with different aspect ratios, but the same inertia. And actually, what you can observe is that the thicker disk doesn't fall with the same style as the thin disk. For instance, if you look at the symmetry axis of the disk, which is marked with this red tick here, you see that this guy actually tends to have its axis aligned with the path all along the path. In contrast, this guy actually tends to have its symmetry axis making a large angle with the path. So in that case, basically, the disks tend to glide along the trajectory, okay? So clearly, these two guys do not perform their fall or rise with the same style. And of course, you can say, oh, but why not try to predict these trajectories simply with potential flow theory? Because it is known that actually potential flow theory is able to predict, well, let's say, free rotation, free translation of a body in that direction. You can find that in Lamb's textbook, for instance. But if you do that, actually, it turns out that the frequency you predict is typically 1 or 2 orders of magnitude larger than the one you observe in real life. And more than that, actually, what you predict is also that in this case, you see the angle between the symmetry axis and the path is always very large compared to what we observe in the experiments. So clearly, this picture is wrong. It's simple, but it's wrong. This is not what happens in real life, okay? So this was the starting point of our studies. So I will not talk more about experiments. So now I will devote the rest of this talk to what we did through theoretical analysis or direct numerical simulation for this class of problems. And actually, we tackled the problem with 3 distinct methodologies. One is direct numerical simulation, and I will talk about this one first. The second one is global linear stability analysis, and I will show you how the two complement each other. We also did weakly nonlinear analysis of this problem, but I will not have enough time to talk about this. So I will concentrate on these 2 approaches now. Okay, so, well, let's state the problem in a very simple way. So consider a disk which is made of a homogeneous material with density rho s. It falls or rises within a fluid which is a Newtonian fluid with rho and kinematic. This disk has a height h and a diameter d, and of course the driving force is provided by gravity g. Okay, with this, you can build 3 dimensionless parameters. One is the aspect ratio key. The second one is the density ratio or the relative inertia I mentioned previously, and I will use this one actually, but you can think about it as a measure of the density ratio. So the larger I star, the heavier the disk, basically. And the third one is what is called usually the Archimedes number, which actually is a Reynolds number based on a gravitational velocity scale, okay? And so these are the 3 parameters that govern the problem. And of course, we have to specify the initial conditions of the problem. And in the rest of what I'm going to talk about, the disk will always be released broadside on, okay? So let's first talk about direct numerical simulation. So this was published a few years ago. And so I have to say a few words about the technique first. Now, I don't want to bother you with the technique, but I think it's important to realize that this is not for free. You have to you have to spend months and years on this before you can get reliable results. So in a few words, basically what we do is that we solve the Navier-Stokes equations for the absolute velocity field, but we solve them in a frame of reference that rotates with the body. During a time step of the computation, we freeze the body velocity and rotation rate. Then at the end of the time step, what we do is that we solve the force and moment balance on the body through what is called the Kirchhoff-Kelvin equations. Then we update the body velocities and rotation rate, of course, and then we update the fluid velocity so as to make the fluid satisfy the no-slip boundary condition at the body surface. Okay, so that's the general numerical strategy. And in this problem, especially with disks, there are two specific difficulties. One is how to deal with the edge here, because the edge is basically a singularity. And so we worked quite a lot in order to make sure that we properly resolve this singularity. So here you see two comparisons between the numerical prediction, which is the solid line, and the theoretical prediction at low Reynolds number, the so-called Moffat singularity prediction. So this is for the pressure and this is for the vorticity. So you see that the two nicely agree. So we are confident that we properly solve what happens at the edge. And the second difficulty has to do with the wake, and more specifically with how does the wake leave the computational domain. Because of course the computational domain has a finite size, and at some point, of course, vortices have to leave the domain without disturbing the motion of the disk. And of course, the difficulty in this problem is that since the body may rotate, you don't know where the wake will exit the domain. So you have to use an outlet boundary condition which evolves over time so as to be applied at the proper location of the domain, okay? And this also gave us a hard time. Okay, so if you have technical questions about this or about anything else I'm going to say, please don't hesitate to interrupt me, okay? So I will not say anything else about the technique, the numerical technique, but if some of you are interested, I can comment afterwards. Okay, so this was the technique. And so now, here are the results. So the results, actually, you may summarize them into this phase diagram. So this is for an infinitely thin disk, which is the one I am going to comment on first. So this is the phase diagram we obtained. So again, the Archimedes number and the disk inertia ratio, okay? So the gray region is the one in which the disk just falls or rise broadside on, and all the colored region correspond to a different non-vertical state, on which I'm going to comment now. So let's first start by considering one point which is here in the gray region, and you will see what happens to this guy. So what you see is a disk falling, so it is basically zigzagging or fluttering if you prefer. And what you see here actually is what is called the lambda 2 criterion, which actually shows you the region of high vorticity in the wake. So I can play it again if you wish. You see that in this case, well, the disk reaches very large inclination angles, but still it's fluttering, it doesn't tumble completely, okay? And maybe a first thing to be remarked is actually that you see that the lowest Archimedes number at which the disk can become unstable correspond to this point here. And if you compute the Reynolds number, the corresponding Reynolds number is about 30. And this is quite remarkable because if now you come back to the case of a fixed disk, so you consider a fixed disk broadside on in a uniform stream, then you will find that the wake of that guy becomes unstable only for a Reynolds number of 115. Whereas if the disk is free to move, it may become unstable for Reynolds number as low as 30. So maybe this is perhaps the most important take-home message I have to deliver today, which is that actually you cannot understand what happens to a freely moving body just by having performed experiments or computations on the same body held fixed in the lab. Clearly, there is a connection between the wake and the path, but the connection is not one-to-one, okay? You really have to deal with the degrees of freedom of the body if you want to understand what happens. The wake itself doesn't tell you the truth. So that's the most important message. So, yes, a way to represent the body motion is to plot actually the vertical velocity of the body versus the horizontal velocity. So this is a kind of phase diagram. And in this green regime, actually, you see that this phase diagram produces a closed loop, which means that indeed this is a periodic motion. Clearly. And well, we can detail this periodic motion. I don't want to spend too much time on that, but basically what happens is that, of course, when the disk is falling like this, its vertical velocity is maximum and the horizontal velocity is nearly zero. And then when the disk tends to become more or less horizontal. Of course, the vertical velocity decreases, whereas the horizontal velocity increases. And at some point, the disk tries to overturn, but actually it doesn't have enough energy to do that. And so this is why actually it changes the sign of its horizontal velocity and it zigzags in the other direction, okay? This is basically what happens physically in this case. So we can now look at the second transition, so the orange region here. So again, this is the same representation, but you see that now the disk is performing full rotations, so full tumbles. And again, you see, well, how the vortices are shed in the wake of the disk. So in this case, if we plot again the vertical velocity versus the horizontal one, here is what we get. So you can compare with the previous plot, this one. So now the disk has enough energy to overturn. So basically its rotation rate doesn't change sign, which means that the horizontal velocity is keeps always the same sign. And you may notice that actually it never goes to zero, which means that there is also a mean drift of the disk. Actually, it doesn't fall along an average straight line. It drifts laterally, which means that through this transition, actually, we have lost the vertical symmetry of the problem, okay? We have kept the planar symmetry because the motion is still planar, but we lost the vertical symmetry. So there is clearly a symmetry breaking associated with this change of state. Okay, so now what happens in the purple region? So maybe it's harder to see because the disk looks quite small in this video, but yes, maybe here you can see it better. Actually, well, there are stages of the motion in which the disk actually tumbles, and at some point doesn't tumble anymore and it flutters, and again it starts to tumble, etc., etc. So what happens in this case is that basically the disk has a marginally sufficient amount of energy to overturn. So sometimes it succeeds in overturning and sometimes it doesn't. And this regime is chaotic, and you can convince yourself that this is the case on this phase plot here, because you see that little by little, actually, the diagram will be filled, basically, will fill the entire view. So clearly we are not in a periodic regime, but in this case we got a chaotic regime, and this corresponds to what was seen by the group of Field and Norrie, the paper I mentioned that occurred in Nature. Okay, so this was basically the knowledge that was got for experiments at the end of the previous century. So we were able to recover that. But actually, we got more than that, because we also got, you see, this regime and that regime, which I am now going to comment briefly. And these two regimes actually are not planar regimes. These are 3D regimes. So it may be a little bit hard to see that they are 3D, but here you probably see it a little bit better. What happens is that basically here the disk is fluttering, but it doesn't flutter in a single plane. Actually, the fluttering takes place in a plane which itself rotates little by little. And so if you plot the full path, you get this. So this is a 3D view of the path. And now if you plot the two components of the horizontal velocity, one versus the other, you clearly see the drift of the plane in which the disk is fluttering. Well, the reason why this was not observed previously in experiments is quite simple. This path actually has a very large pitch. Basically, it takes more than 60 times the disk diameter to perform a full revolution. And basically, most experiments have been performed in tanks which were only 50 diameters high. So you need a very, very high tank to see really this trajectory in a laboratory experiment. So, and by the way, we had to run this computation probably for 3 months to see it. And so same thing with this helical tumbling here. So again, by performing very, very long computation, we were able to obtain this kind of trajectory. And again, if you plot the two horizontal components of the velocity, you see what happens here. So basically, the disk now is tumbling, except that instead of tumbling in a single plane, actually, the plane in which it tumbles is rotating little by little. And after a very long time, you can get a full circle here. But this, of course, takes a very long time, since well, actually, to get a full revolution here, you need basically 400 to 500 times the diameter. And so this would represent a very, very tall tank in an experimental device. Okay, so this was never observed previously in an experiment for these reasons. Okay, so that was the story of the styles of fall or rise. But what is particularly interesting is what happens for low disk inertia, which I'm going to comment in a little bit more detail. So I will now concentrate on this region where the inertia, the relative inertia of the disk is low, and especially I will follow this dotted line here and see what happens when the Archimedes number increases, okay? So here is basically what happens. So what you see on this graph is actually the instantaneous Reynolds number of the disk. So you can basically think about it as if it were the instantaneous vertical velocity of the disk as a function of the Archimedes number. Of course, the two extremities correspond to, well, the extremities in the motion of the disk. So starting from a low Archimedes number here, we are first in the steady vertical regime, so the disk is falling like this, simply. And at some point, increasing the Archimedes number, we enter this red regime here, which is actually a very, very low amplitude spiral regime. Then if we increase the Archimedes number a little bit more, we get another but different low amplitude spiraling motion. And then if we increase the Archimedes number further, we get a small amplitude planar regime. So these two were 3D, but this one is a planar regime. And then at this point, suddenly, we enter this large amplitude zigzagging regime, okay? But if we now are in this green regime here and decrease the Archimedes number, actually, what we do is that we follow we are still in the large amplitude zigzagging regime down to this point here, which means that actually all this region from this point to that point here is a region where bistability takes place. And you can also appreciate that if you look at the instantaneous inclination angle of the disk. So in this 3 low amplitude regime, the maximum inclination angle is very small, a few degrees. So you see 2 degrees, for instance, here. And then suddenly, well, you jump from this small inclination to this very large one. So this corresponds clearly to a subcritical bifurcation. Clearly, there is a large domain in which 2 states may coexist, and this is a distinctive mark of subcritical bifurcations. So there is a large region where bistability exists, as I said, and so that was the first thing we discovered when we tried to increase the Archimedes number. And of course, we were in particular interested in this 3rd small amplitude regime, which takes place here, because this is a regime which corresponds to this pink region here. And let me show you how it looks like. So you see that clearly there is vortex shading past the disk, but the disk itself, actually, you get the impression that it is falling in straight line. Actually, it is fluttering a little bit, but in an experiment, it's really very hard to see that. But clearly, in this regime, there is very little connection between what happens in the wake, where there is clear vortex shading, and the reaction of the disk. Okay? So next, we address the question of what a thin disk is. What I told you up to now was for an infinitely thin disk, but then we decided to consider what happens when the thickness is small but finite. Indeed, if I come back to this phase diagram from 1997, all data that are gathered in this diagram belong to disks with various thicknesses. At that time, everybody was convinced that a disk with an aspect ratio of 10 or 50 or 100 was the same thing. Provided the disk is thin, and it's the same. So basically, this diagram gathers very different disks. And so, of course, we ask the question, what does DNS have to say for this? And we run the DNS for a thin disk, but with a finite aspect ratio, so k equal to 10. And here is what we obtain. So this is a reminder of what I just told you for a disk with an infinitely small, large aspect ratio. And this is what we get for an aspect ratio of 10. So first, actually, the critical Archimedes number at which the large amplitude zigzag takes place is about 65, whereas in that case, it was half that. So clearly, that's very different. And what is also very different is the succession of small amplitude regime we got in this case. Actually, we got 5 instead of 3. And the first 3, actually, in this case, they are planar, whereas the first 2 here, they were 3D. Then the first regime here is a stationary regime. I will comment on it a little bit later. It corresponds to a steady oblique path like this. So it's a stationary regime, whereas in that case, all these regimes were time-dependent. So clearly, the 2 pictures are totally different. And I can tell you a true story about that. Actually, when we got these results, the PhD student came to my office with the 2 sets of results. And I said, well, no, that's not possible because an aspect ratio of 10 is already a very thin disk. So we should, well, the 2 series of results should match. So there is something wrong in the code. So go back to your office, check this and that, etc., and you will come in a week to tell me what was wrong. He came 2 weeks after, said, Well, I checked everything. I couldn't find any error, so I don't know where to go. I said, no, it's not possible. Something is wrong in the code. I cannot believe this is true. So check this one, well, the outer boundary condition, check how we treated the edge, etc., etc. He spent another month on this, and that was totally unsuccessful. He came back and said, no, it's like this. He said, okay, I don't want to waste the rest of your PhD by checking the code, but we cannot publish these results because I'm totally convinced they are wrong. Something is wrong somewhere. So we stayed with the results on the desk without publishing them during probably 2 years. And I will tell you later how the story finished. But this is perfectly true. Okay. Doesn't want. Doesn't want to obey. Okay. Okay. Oh no, I see. Okay. Okay. So I will not say more about what we got with DNS, except that you have to keep in mind the first part of the true story I just told you. And now I'm going to tell you more about the global linear stability analysis. So the same problem, but this time it will be seen from the point of view of linear stability analysis. So, well, linear stability is well known. Basically, well, you expand all fields in the problem in terms of a base state and a disturbance. So in this case, well, the base flow is governed by the stationary Navier-Stokes equation here. And so we have to solve this, this steady Navier-Stokes equation. We do that with a Newton fixed point method. And for instance, what you see here is a result for the base flow for a disk, which is held fixed at a Reynolds number a little bit larger than 100. So the disk is here, the flow is coming from left to right. And what you see is actually the pattern of streamlines and the actual velocity disturbance. Okay? And then, of course, once you get the base state, you have to write down the set of equations for the disturbance. So this set of equation comprises the linearized Navier-Stokes equation, of course, which involved the influence of the moving disk. So this is the translational disturbance to the disk velocity. This is the disturbance in the rotation rate, etc., etc. This is actually the force balance on the disk, which involves the disturbance in the stresses applied by the flow. And there is also, of course, a disturbance due to the gravity force, because since the disk is moving like this, of course, and gravity is always vertical. Actually, when you project gravity onto the disk axis, well, you get varying component. This is the torque balance on the disk, and this is actually the relation that connects the rotation rate to the inclination of the disk. So all this set of equation governs the linear disturbance. Of course, you have to apply boundary conditions, but basically what you see here is that actually the flow is forced by the disk motion through these terms and through the boundary conditions, and the force and torque balance is forced by the flow through the stresses here, okay? So how to deal with this problem? Basically, you have 5 series of unknown: the fluid velocity disturbance, the pressure disturbance, the disk velocity disturbance, rotation rate, and inclination. So these are what we call fluid variables, and these are solid variables. We expand all these variables in the normal form, in the usual normal form. So lambda here is the eigenvalue. It has a real part, which is the growth rate of the disturbance, and an imaginary part, which is actually, in case it's non-zero, it's the frequency of the disturbance. And we take advantage of the fact that the disk is axisymmetric to expand actually all fluid variables into azimuthal wave numbers with number m here. And so we solve the problem that is this problem here with these 5 equations. We solve it thanks to FreeFem++ software, which is an open software making use of finite element. It's a French software. Yes, it was set up in Paris, but it's available, and it's more and more used by people in fluid mechanics, especially for stability studies. And so basically solving this problem means that you have to solve a generalized eigenvalue problem, which you can condense in this form. So the AM and BM are big matrices. Of course, you have different matrices according to the azimuthal wave number you consider. And actually, each of these matrices is made of blocks, big blocks. So basically, the red block here is just connecting, well, the various degrees of freedom of the fluid itself. So basically, the connection between this and that just tells you the response of the fluid. The green block is connecting the solid with itself, and the yellow blocks are actually connecting the fluid and the solids. So this seems to be a huge problem. Fortunately, there are many simplifications, and for instance, it can be shown that the mode m equal to 0, which is the axisymmetric mode, is always stable in this problem, so we don't have to care about it. And you can also show that all modes with m equal or larger than 2, they may be unstable, but actually they don't give rise to any change in the body motion, actually, because actually the yellow terms turn to be 0 for all these higher order modes. So the only mode of interest for us, in order to understand why the fluid is able to disturb the body motion, is the mode m equal to 1, on which we concentrate later. So once you solve this eigenvalue problem, you get this kind of thing. So this is for one disk, infinitely thin disk, and for one specific inertia. And actually, what we see here is that we got 4 modes, 4 relevant modes, the yellow one, the blue one, the black one, and the purple one. And for instance, if you increase the Reynolds number, you see that the first mode, which gets a positive real part, is the purple one, actually. So the lambda r becomes positive at this point. So you see that this mode is unstable in this region here, but then at some point it restabilizes, and again it becomes unstable here, and remains unstable even for a very large Reynolds number. But then if you come back here, there is a second mode here that emerges and becomes unstable at this point. Then there is a third one which emerges and becomes unstable there, etc., etc. And if you look at the imaginary part of these modes, actually they are all different. You see that the yellow mode has basically a Strual number which is about 0.1, whereas the purple one has a Strual number of 0.25, and the black one actually has a 0 Strual number, which means that this is a stationary mode. Okay, so this is the kind of information you get by solving the eigenvalue problem. But with this, what you can make, which is more interesting, is build actually a neutral curve. That is, now you vary the inertia ratio of the disk, and you get this neutral curve here. So the gray region is the one in which the motion of the disk is stable. And beyond, of course, this neutral curve, actually, this is the unstable domain. So what you see here is that actually the neutral curve in this case is made of 2 modes. Up to this point, actually, this is the yellow mode, So the one that becomes unstable here, it is a yellow mode. So for this low inertia disk, it's the yellow mode that is unstable first. But then beyond this point, if you increase further the disk inertia, it is the purple mode that is most unstable, okay? So clearly there is a crossing of modes at this point. And what we can observe here, we can make several observations, of course. We can say for instance that the critical, in particular, the critical Reynolds number is almost constant up to this point, and this is true also for the Strouhal number. Whereas, of course, for disks with larger inertia, this is not true anymore. Of course, another remark of interest is that if you perform the same analysis for a fixed disk, actually, you don't get 4 modes. You only get 2 modes, which means that among these 4 modes, 2 are due to the fluid and 2 are due to the degrees of freedom of the solid. Okay? They don't have the same origin. They play together, they are coupled, but they don't have the same origin at all. Okay, so now what you can see also, what you can extract from this neutral curve also is that, of course, when you increase the disk inertia and cross this point, of course, regarding the frequency you will observe, you experience a big jump because remember that the yellow mode has the frequency with the Strouhal number, which is about 0.1, whereas the purple one has a frequency which is 2.5 larger. So by just increasing a little bit the disk inertia, in this region, actually, what you observe is that suddenly the frequency of the oscillations of the disk, they jump from a Strouhal number, which is 0.1, to one, which is 0.25. Okay? And this is just because actually the first mode, which is unstable in that range, is different from the one which is first unstable in that range. And this you cannot understand with the DNS. You can see it with the DNS because the DNS tells you the whole story, but it doesn't help you to understand what happens. And this is actually a real outcome and a real plus from the global linear stability analysis. Because with this analysis, by expanding everything in terms of normal modes, you understand that actually there are several modes that play together, that one is winning in some part of the domain, another one is winning in another part of the domain, and of course, when they cross, there is something more complex that happens. But this is really what you can get with the global linear stability analysis. And now, of course, if you compare the prediction of the linear stability analysis with those of the DNS, this is what happens. Actually, this is, so the S1 mode is the purple one, you see. So when you plot the prediction of the linear stability analysis for this mode, you get this curve, and you see that throughout this intermediate range of inertia, this is very close from what we get with the DNS. And then the F1 mode here is the yellow mode, which is here. And so you see that the yellow mode is this one. And you see that for disk with small inertia, actually, this is also very close from the threshold predicted by the DNS. So clearly combining these two modes provided by the linear stability analysis allows us to recover almost perfectly the border of the unstable domain that was determined by the DNS. It doesn't allow us to recover it here because actually in that range, the bifurcation is subcritical. But for the rest, actually, the two set of predictions are in very nice agreement. I am coming to that. Yeah. Okay, so yes, the answer will be in the next slide. So yes, of course, we can do more because if you do global linear stability analysis, it means that, of course, you determine the eigenvalues, but you also determine the spatial structures of the mode. And you can actually use that to get more insight into the problem and into the dynamics, the coupled dynamics between the fluid and the body. So, for instance, you can look at the distribution of the axial velocity and axial vorticity disturbance past the disk, and you can normalize all these disturbances by the complex inclination of the path and observe the resulting structure for two different inclinations. For instance, when the inclination is maximum and when it is zero. And basically, what you can expect is that if the two pictures are very similar, it means that whatever the inclination of the disk is, well, the structure of the fluid is almost unchanged. So little coupling between the disk and the fluid. In contrast, if the picture you get when the inclination is maximum totally differs from the one you get when it is zero, then clearly there is a strong coupling between the disk and the fluid, okay? So here is how it looks. So for instance, this is the structure of the mode at this point here. So this is where what we get when the inclination is maximum. This is when it is zero. So the upper part of each figure is actually the axial velocity disturbance, and the lower part is the axial vorticity. So basically, if you concentrate on the upper part, you see that the structure is almost the same in both pictures, okay? So in that case, it means that whatever the inclination of the disk, you get the same fluid structure, so you can conclude that the coupling between the disk and the body is very weak. And indeed, this corresponds, so this point actually corresponds to a point here. Actually, in that case, it's a regime in which, yes, there is vortex shading in the wake, but the disk is only very weakly fluttering. So yes, there is very weak coupling between the two in this case. Now, compare with that one. So it's the same disk, but now we are looking at what happens at this point. So here is the structure of the axial velocity disturbance when the disk inclination is maximum, and here is the structure when the disk is zero. You see that the two are totally different. Here, actually, throughout the wake, you get the same sign of the disturbance. So we call it a sign-preserving type disturbance. In contrast, here, you get an alternation of positive, negative disturbance, etc. So it's a sign-alternating type disturbance. And clearly, the fluid feels what happens for the disk. That is, if the disk changes its inclination, then the fluid reacts to that. Okay? So in this case, there is really a strong coupling. And of course, this corresponds, in this diagram, this corresponds to a point which is located more or less here. And indeed, this is a large amplitude zigzagging regime. So yes, we can learn many things by looking at the spatial structure of the global modes. And to end this talk, I will comment on what happens with disks of finite thickness. So I will examine successfully what happened with key equal 10 and key equal 3. So here is the neutral curve for key equal to 10. So what you see is that here, actually, instead of two modes, actually, the neutral curve is built on three modes. First of all, when you start with very light disks, the first mode that becomes unstable is a stationary mode, so zero frequency. It means that actually the disk is falling like this, but it doesn't oscillate at all. Then there is an intermediate range here within which actually the mode that is most unstable is the yellow mode. And then after this point, there is actually a third mode that becomes more unstable. So three modes are encounter as you increase the disk inertia. And by the way, you can also remark some things, is that if you select an inertia here in this range and you increase the Reynolds number, so here the disk is stable, then here it is unstable, but again, if you increase the Reynolds number again here, it becomes stable again. And you have to increase the Reynolds number beyond a second value here to recover instability. So there is here a destabilization, restabilization zone in this diagram, okay? And of course, if you look at the frequency, what happens if you are in this range, since the most unstable mode is a stationary one, actually the Stroll number is 0, then suddenly you cross this point here, and the most unstable mode is this one, which has a frequency, a Stroll number, which is about 0.15. So you see a huge jump in frequency. And then when you cross the second point here, actually the most unstable mode is the purple one, which has a frequency which is about 0.07 or so. So again, there is a strong jump, or rather fall in that case, of the Stroll number. Okay, and again, if you look at the DNS results, you see all this, but you don't understand what happens. You just see these jumps, and you say, oh, what happens in my numerics? And again, the linear stability analysis allows you to understand what happens. It allows you to see that, yes, several modes are playing together, and one is more unstable in this range, one is more unstable in that range, etc. So, and by the way, this will end my initial story with the student, because now we are with this aspect ratio of 10. And so if we come back to what we saw, to what we saw in the DNS, so we had this diagram I showed you before, and remember that what we got now with the linear stability analysis is that the first mode that becomes unstable at low inertia is a stationary mode, which means that you get this kind of velocity disturbance when the inclination angle is maximum, and you get 0 when there is 0 inclination. And remember that actually the DNS told us that yes, the first low amplitude mode that is unstable is a stationary one. So indeed, the DNS was right in predicting this, but we had to wait until we got the results of the linear stability analysis. 2 years after the student, this poor student, finished his computation to understand what happened. So when we got these results, I said, okay, you were right, now we can publish this. So fortunately, the student was still with me. He was doing a postdoc on another subject. So he got a paper on this, and he got also, well, the right to say that, well, I basically bothered him during 2 years for something, some bug which didn't exist at all. Okay, let me finish with the thickest disk, the one with an aspect ratio of 3. So here is, again, the neutral curve we get. So here, again, there are 3 modes, because there is an intermediate range here in which the most unstable one is a stationary mode. But remember that with k equal 10, the stationary mode was the one that was most unstable for very low inertia, whereas here it is the one which is most unstable for intermediate inertia. So again, we have 3 modes, but you see that they don't appear in the same order at all. There is no destabilization, restabilization region left, in contrast to what happens here. So you see that this guy with an aspect ratio of 3 is totally different from the one with an aspect ratio of 10. What else? Well, no, this is the most important message here. And yes, what is important also is that we could, for this case, that is this aspect ratio, we could make a very careful check for specific value of the inertia ratio, because for this inertia ratio, we have three sets of information available. One are our early experiments, the one I showed you at the very beginning. One is the DNS, and one is a global linear stability analysis. And you see that regarding the critical Archimedes number, all three of them agree very nicely, and it's true also for the Stroll number. So for this case, I cannot pretend that this is the same for all cases, especially because actually in the experiments, we didn't explore a lot of inertia ratios, but at least for this case, where the three sources of data are available, yes, we got a very nice agreement. So we can combine all results obtained with the linear stability analysis in this diagram. So here is actually the neutral curve, well, for the three aspect ratio. So you see the infinitely thin disk is the red one, then this is the intermediate one, and this is the thickest one. And you see here the same for the Stroll number. So clearly, there are many things to be said here. For instance, for this with large inertia, of course, you see that the largest the aspect ratio is, the lower the critical Reynolds number is, and this is what you can expect naively. So this is true for high inertia disks, but this is not true anymore for low inertia disks, because you see here that, well, the least stable one is the thinnest one, but actually the most stable one is not the thickest one, is the intermediate one. So nothing to do with the naive view. So this is for the first thing. Then actually also what is to be remarked at low inertia is the nature of the first non-vertical motion. It totally depends on the aspect ratio, because of course it is a stationary bifurcation in the case of the intermediate aspect ratio, but it's also a large amplitude zigzag in the case of the thickest disk, so the red one, and it is the purple one, sorry, and it's a low amplitude zigzagging motion in the case of the intermediate disk. Okay, so clearly you cannot, on naive basis, you cannot predict what happens when you vary the thickness of the disk. And you have to turn to the linear stability analysis to tell you what happens. So let me conclude, because I think I was pretty long. So I hope I convinced you that for this family of problems, direct numerical simulation and linear stability analysis nicely complement each other, although of course the range of validity of the linear stability analysis is much more narrow, because it's it's valid only close to the threshold. But at least linear stability analysis allows you to understand why the changes of style and frequency you observe in the lab or on the computer when you perform a DNS occur. Otherwise, you have no chance to understand why. So, second point is, of course, that, well, falling disks, they have a very rich dynamics, especially when they have low inertia, because, of course, at low inertia, they are much more sensitive to the fluid. And as I said before, probably the most important message is that, and this is true not only for disks, this is true for any bluff body at least, is that you cannot reduce the dynamics of a freely moving bluff body to the dynamics of its wake. The wake is very important. The wake, of course, is the region where vorticity is produced, and it is, of course, the region that determines a lot of characteristics of the instability, but actually the coupling with the degrees of freedom of the body are crucially important. If you forget that, you cannot understand, for instance, that the threshold for the first instability for the disk or the sphere may be in some regime much smaller, much lower than the one you get for the same fixed object. So that's probably the most important message. So what we did after that work is that we applied the same, let's say, the same technology to bubbles as well. And we also performed some, as I said at the beginning, some weekly nonlinear stability analysis. And that was quite helpful to understand, for instance, why in some cases we get planar trajectories, whereas in other we get 3D trajectories. So weakly nonlinear analysis can tell you that, because actually under certain conditions you can compute exactly the coefficients involved in the amplitude equations by performing the relevant dot products in the Navier-Stokes equation. We also did the same thing through DNS on very light spheres, and actually that was a total nightmare, because you may think that spheres are much simpler than disks, but because there is no singularity, there is no edge, etc., etc. But actually, spheres are real devils. And spheres are real devils because actually they are supposed to be perfectly isotropic. And if you do lab experiments, your spheres are never perfectly isotropic, especially if they are very light, because actually the material has some inhomogeneity or something like that. And you can say, okay, but in the DNS, you can draw perfectly isotropic sphere, which is true. But your grid around the sphere will never be perfectly isotropic. Think about a spherical grid. If you are close to the axis, you get small cells. If you are close to the equator, you get big cells. So this introduced an anisotropy in the problem. And we had to fight during several years to make our computations reasonably isotropic. So we ended up with, I think, a good bunch of results which were published last year. And now we are playing with a more exciting problem, which is actually the linear stability analysis of deformable bodies. So for instance, flags, drops, and bubbles. And one student just completed his PhD on that, but the paper is still to be written. Okay, and with this, I have to thank all of you very much. And especially I have to thank my two outstanding PhD students. So this one who was the poor one I pestered during 2 years, and this one who is now doing a postdoc in Berkeley. Okay, with this I have to thank you very much for your attention, and I'm ready to take your questions.
Thank you, Jacques, for that very exciting lecture. We can have a few questions. There are some mics here, there, and there. So please go to the nearest mic and don't feel shy. Ask questions.
Now I can handle this one.
Yeah, actually, I wanted to know, why is this whole experiment just performed on disks and not...
Sorry, I cannot hear you.
I wanted to know why this experiment is performed on disks and not something else, like any other object, like a cube or something.
So you ask why we selected disks.
Yeah.
Well, I would say maybe first because, there are several reasons, actually. Well, it's easy to manufacture. It's much more easy, for instance, than ellipsoids or spheres. Well, at least at the time we did the experiments. Now with 3D printing, it's different, but at that time it was much easier. You just have to take a rod of the material you like, and you cut it, etc., and you polish it. Yeah, okay. Then, in terms of numerics, it's also quite easy, although you have to deal with, of course, with the singularity at the edge, but it's pretty easy to design a grid, etc., etc. And and maybe this is the most interesting reason, actually, you find this in a variety of applications, because there are many processes, including actually natural processes in the ocean, in which you find bodies which look more or less like disks, and that freely rise or fall within the medium, so within the ocean or within the atmosphere. Okay, so it may be seen as a prototype of anisotropic bodies for which this kind of dynamics is observed. Oh yes.
So I'm not sure whether this has like that much applications as the disk itself, but if you would make a hole inside, how does this affect stability, like a hole of various sizes?
So yes, this is a very sensible question, and actually it was addressed by a group in California recently. So there was a paper by the group of Eva Canso in the journal Fluid Mechanics, probably 2 years ago or something like that. And actually, well, to make the story short, most of the time it plays in favor of stability. That is, it delays instability. Of course, you can get instability. So if you take a coin and you drill a hole in the center, you will get your coin, well, zigzagging or tumbling also. But you have to wait for larger inertia ratios or larger Reynolds number. So basically, it plays in favor of stability because it allows fluid to go through the center instead of having to go around the edge.
Hello, sir. Just curious to know, if you add rotation to the disk, what new things you might see?
So you, so what do you have in mind? Initial rotation or
like you apply a constant angular rotation to the disk? So
but all along the path. You force it.
Or maybe you initially apply some rotation, then let it fall. So
okay.
What will happen? Some question.
Well, I have to stay careful. Yeah, because, well, it depends. Well, basically, what I can say, because, we played with that in experiments a little bit. So if you are close to the instability threshold and you just apply an initial rotation, okay, it changes the initial stage, but after some time, well, you recover the same dynamics. Now, if you are further away from the threshold, I wouldn't say that. And I don't know what happens. Because, of course, basically, this is a different initial condition. And remember, at the beginning of the talk, I said, all the disks I'm going to talk about, they were released both sides on. And in the experiments, we also did our best to avoid any disturbance, etc., etc. So if we are pretty far from the threshold, then this different initial condition can give rise to totally different dynamics. So I have no idea.
Okay, thank you, sir.
I wanted to know even like in what scenarios don't the Navier-Stokes equation are not defined? In what scenarios are they not defined? Like
what do you mean?
How much can we control the situation?
What do you have in mind regarding the validity of the Navier-Stokes equation?
Yeah, like.
But you mean in terms of the minimum size at which they are valid, or,
yeah.
or minimum maximum size, etc.
Like what is the the extreme ends of
of the validity of Navier-Stokes equations. Okay, so this is a very general and interesting question, far beyond the talk. But actually, well, maybe some people in the audience have different answers, but what I can say that from what I know, nowadays we can say that they are valid down to distances of a few nanometers. So at least at 10 to the, when you have characteristic lengths of 10 to the minus 8 meters, they are still valid. And if you go to very large distances in astrophysics, actually they are valid even over distances of several thousand of kilometers. So which means at least 10 to the 8 in terms of meters. So which means 16 order of magnitude. Okay, and this is probably a lower bound because there are some, well, not some, but at least I know several astrophysical processes in which they are valid even for over larger distances. But maybe some colleagues in the audience have different answers. But yeah, this is one of the beauty of fluid mechanics, actually. You have a set of equations which provided you have a simple fluid, are valid over a huge range of sizes. And with the same equation, you can look at problems in extremely different ranges of distances, which means in very different ranges of applications. So be convinced that there is a future for fluid mechanics. That's the message.
A last chance to ask a question. Yeah.
Hello. Thanks for your talk. So in all your experiments, if you just take away gravity completely, how does it change things?
Well, there is no driving force left in the problem. So what do I have to do? So I have to replace gravity by some other force. By the way, actually, well, you can think about some extra body force different from gravity. Of course, gravity is the simplest and the most common. But for instance, if you think about I don't know an electrical field of something like that, you can play with the same kind of dynamics. Or provided your body is sensitive to some body force, then you can get the same kind of dynamics. But you need a driving force in the system.
Right. No, in the case of, say, bubbles rising.
Yeah, but it's the same. It's buoyancy, but because basically, well, the case of bubbles actually, and I've worked a lot on this actually. That was my entrance door to this subject, actually, because I wanted to understand what makes bubbles rise in spiral or in zigzag, okay? So that was some 20 years ago. So in that case, basically, the bubble is an inertialess body. It has almost no inertia, but it is surrounded by a fluid which has large inertia. And of course, it has to adapt to the disturbances the fluid apply to it, okay? So this is exactly the same family of problem, really. Yeah.
Okay, there is high tea waiting outside for you, and you could also try to catch Professor Magnaudet. So let's thank him once again for this delightful.
Thank you very much.